write down the Newton's second law along x direction, y direction, these things, right? Even though you may not be able to solve it to get the answer, you wouldn't lose many points if you do that, okay? For example, if you do the kinematic problem, you have kinematic equations. If you write down the known quantity, you write down the kinematic equations, even you don't get the result, you still should get most of the points. So pay attention to those standard procedure. So here, our key idea is that we want to describe the motion. So we want to find like, so what is the final velocity, what is the final displacement with some given quantities. And then usually we have this kind of stuff. If we want to calculate like final velocity or something else, delta x, these things, okay, we have to know the acceleration here, okay? But how can we know the acceleration? We have to do the force analysis. Okay? So here, from force to the acceleration is the Newton's second law, F equals to ma. But we know that to apply the Newton's second law is not that simple. If here is the net force, you may involve many force, 2 or 3 forces, and they may be in different directions. So you have to decompose them into x direction, y direction. Okay. So this is called the force analysis. And then here, usually you can use kinematic equations. Kinematic equations to solve for the okay, you know here if you have 3 known quantities, you can solve for any other quantities. Okay. This is the general procedure. And so we know Newton's second law, okay, plays a very important role in the study of the mechanics because it relates the force to the acceleration. And once we have acceleration, we can calculate other quantities. Okay. Now, in this unit, our hope is try to do something like this. Bypass the explicit calculation of the acceleration. Okay, so that means we can somehow bypass a lot of complicated math manipulations. If we can do that. Okay, so then we have to introduce, okay, like work, energy, impulse, momentum, these new concepts. So you can see here, nothing is free. If we want to reduce the complexity of the math calculation, the price we're going to pay is that we have to introduce more physical concepts. Okay, and these concepts may not be very, sometimes they can be quite abstract. Okay, so in this part, more importantly, you have to pay more attention to the understanding of these concepts or how to set up the problem. In this part, you have to choose equations from many equations. Okay, for previous parts, basically you don't have a lot of choice. Every time for most problem you use Newton's second law. Okay, but now you have to choose from many equations you can use. Okay, now let's first introduce the needed quantity. Okay. The first physical quantity we want to introduce is the work. Let's look at if you have a constant force F, and then if you try to calculate the work done by the force F, what's the definition of the work, mathematical definition? Okay? And it says that W, okay, what's that? Equals to F parallel multiplied by P. What do you mean by the F parallel? Okay, basically it says that if you have some object, you use some force to pull it, and under this force, if the object moves a distance P, okay, And then the work can be calculated as force multiplied by the distance, okay, the traveling distance, d. But there is one thing you need to pay attention to. To calculate the work, we can only use the components of the force along the direction of the motion. Okay. So you may pull the object in this direction. So the force, okay, is along this direction. If it equals to, like, say, 50 Newton, you cannot use the 50 Newton here, put it here to calculate the work if the distance equals to 10. So the work is not 50 multiplied by 10, okay, 500. This is wrong. Because we need, so what we have to do is that we have to decompose this force to get two components. This is one component. This is another component. Okay, we can call the two components. Okay, instead of call them x and y, we'll call them f parallel and f perpendicular. Okay, so one component is parallel to the direction of the motion. Another component is perpendicular to the direction of the motion. Okay, so to calculate the work, you only want to consider this part. Okay, and for example, if it's equal to 40 Newton, and then the work has to be calculated from 40 multiplied by 10 equals to 400, something like this. Okay. Any question here? And this component, the perpendicular component, wouldn't contribute to the work. Okay? Any question here?
Now, if you were concerned in the direction that perpendicular, you wouldn't worry about parallel, you would just consider the perpendicular, right?
What do you consider perpendicular?
Like if you were moving straight up instead to the right, you wouldn't worry about.
Okay, so in this case, note that how would like you to express this problem. If the object is moving upward and the force is to this direction, okay. After decomposition, I'm going to call this is F parallel, right? And then this is F perpendicular. Please note that these notations, they are relative notation. Parallel means parallel to the direction of the motion. So if the direction of motion is upward, then this component is F parallel. And I'm going to use this component to calculate the work. Okay? Now, let's look at, in fact, we can further write down the equation as W equals to F multiplied by D multiplied by cosine theta. Why? Here, if the motion is to this direction, for example, and the force F is to this direction, okay, and we try to find the parallel component, F parallel, okay, and we know the angle between the force and the direction of the motion is theta. You can see with the standard rule of the vector decomposition, this component should be written as F multiplied by cosine theta, right? Okay. And then if you put it into, so that means F parallel multiplied by D equals to F cosine theta multiplied by D is F T cosine theta. Okay? In this equation, you can use the original force F, 50 Newton, and the distance D. But then, you are going to put this fact. Okay, don't forget you have to put this fact, the cosine theta. Okay? This one actually comes from the vector decomposition. Now, one thing we need to pay attention to the theta is that this is not the orientation angle of the force. This is the angle between the force and the direction of the motion. Okay. In this case, this theta equals to the orientation angle of the force. But I'm going to give you another situation where theta will not be the same as the orientation of the angle of the force. So for example, okay, this is your coordinate. And now the object moves along this direction. Okay, D. And the force is along this direction. So the object moves like this. Suppose the orientation angle here for the force is like 60 Newton or 60 degrees. And the angle of the motion is 20 degrees. Okay, so this is 60, this is 20. And then what is the angle you have to put to calculate the work? Here, what is the value of angle theta here? 40 degrees, right? It's the angle between the two directions, this angle. So it should be 60 subtract 20. Okay. So that's very important. You have to remember that this angle theta, by definition, is the angle between two directions. Okay. It may not be the angle measured from x-axis. So some comments about the work. First, it's a scalar. Okay, that's a good thing. The calculation of the scalar is always very simple, straightforward. Okay, your algebraic manipulation. In fact, that's kind of determined by the side of cosine theta. Okay. And physically, that means it's determined by the relative direction of the two quantities, the direction of the motion and the direction of the force. For example, if the angle here, if theta is greater than 0, smaller than 90 degrees, okay, if it's a acute angle, this is f, this is distance. We know that if angle is between 0 to 90 degrees, cosine theta, what is the value of cosine theta? Should it be positive or negative in this range? Positive, right? So if this is positive, then you have positive multiplied by positive. So W has to be positive, right? Okay, so this is positive work. And then if the angle is something like this, if theta is greater than 90 degree, smaller than 180 degree, okay? We know that in this range, cosine theta should be always negative, right? Okay? And then W has to be negative. Positive multiplied by positive multiplied by a negative number. So this has to be a negative quantity. Okay, so this is positive work. This will give you positive work. This will give you negative work. Okay, and so basically you can understand this means this force will give you some positive contribution to the object because it's roughly in the same direction of the motion. And this one, it will give you some negative contribution to the motion because it's roughly opposite to the motion, right? Okay. Now let's consider some limiting case. First here, if theta exactly equals to 0 degree, you can see what happens. In this case, cosine theta, cosine 0 degree equals to what? 1. Okay, and then W equals to F multiplied by T. That corresponds to this situation. This is the direction of T, the distance. Force is also along this direction. Okay. In this case, all the forces contribute to the positive, give you a positive contribution to the motion. Okay. So in this case, if m equals to 0, w equals to ft. Another case is you consider another limiting case. If angle theta equals to 0 degree, 180 degree. Okay. So that means this is the direction of the motion. This is the force. They're completely opposite to each other. In this case, what is cosine theta? You remember cosine 180 equals to cosine 180 degree? Negative 1. If you put negative 1 here, then W in this case equals to negative FD. Okay. So there are some special case. If you know that in the same direction or in the opposite direction, you can directly write down the work in this form or this form without looking at angle. Okay. And in this case, you can understand that in this case, because the force is completely opposite to the motion, so all the forces contribute negatively to the motion. Now, there is another important spatial case. It's between the two situations. If the angle theta equals to 90 degrees, so if this is motion, this is force. Okay, what is cosine 90 degrees? 0. So what is work? 0. Okay. So this is a very interesting case. In fact, it's very important for many analysis. So it will always give you 0 no matter how large the force is, no matter how large the distance is, right? Okay. If the force is perpendicular to the motion, this force wouldn't do any work. Okay. That's very important because we have a lot of perpendicular force in our analysis later. And you can directly tell, okay, if this force is perpendicular to the motion, the work is 0. Okay, you don't even have to calculate it. Okay, any question here? So please understand these situations. All important is this quantity, is note that. Okay. Now, the work we define here is the work done by a particular force. And you may have more than one forces acted on the object, okay? And then we need to find out the total work or the net work. You have two different methods to find the net work, okay? One method is that if you have several forces acted on one object, okay, we know how to find the net force. Remember that, okay, by the vector addition, we can find the net force. Once you find net force, you can resort to this equation, okay, to calculate the net work. Another way is that for each of the forces here, you can use that equation to calculate the work. If you have work F1, you can calculate W1, and then you have F2, you can calculate work W2. You have F3, you can calculate work W3. Okay, with that definition, and then you add W1, W2, W3 together to get the total work or the net work. Okay, so two different ways to do the same thing. And for this, okay, usually it's easier because finally, when you add W1, W2, W3, because work is a scalar, so add them is simply the 1 plus 1 equals to 2 stuff. Okay, so it's much easier than vector addition if you want to add the forces together to find the net force. Now,